Cheers, everyone. Cloudfather here. Today we're going to do a whole bunch of mad science. Part of the fun is to actually do things that you don't think are going to work. And so one of the things I've been playing with, of course, is cork. I just bought some last week for the first time. And one of the problems you have with cork is it absorbs water, and just about anything else is a liquid. So I've been experimenting with various different methods to improve the durability of the cork. Cork also, when you do a dark engrave, has a lot of soot on it. So I'm still trying to figure out how to minimize the soot, which I'm doing by reducing power and increasing speed. But I'm also looking at when I spray this stuff, for example, with the clear that I'm using, which is Rust-Oleum gloss clear, I'm looking at, can I seal this? And what I'm doing is increasing the amount of clear that I put on as I incrementally coat both sides of these cork coasters. And the ones that you're looking at right now, you notice that they have deformed. Well, once the material has dried, they actually flatten out. Now, the other thing that I'm going to do is once I think I have enough clear coat on these, is I'm going to put them between two pieces of mild steel plate, which is about 2.5 millimeters thick. And this provides both a cold surface, but also a fairly heavy surface to flatten this out. So part of the mad science will be figuring out how we can flatten them and seal them. So as we move over to the work table, bought a bunch of new weird materials. So I went to Benjamin Franklin and got kind of a mixed bag of leather materials. I haven't worked with leather since I was probably 8 or 9 years old, so it's been a few years. I have kind of a variety here, and we're actually going to do 50 millimeter test squares on these, just as we did for the laser, pocket stuff that we did earlier in the week. Another thing that I did is I've bought various different forms of cork, and so I'm experimenting with cork products to see, well, how can I cut them? What kind of backings do they have? What kind of thickness? Are there different types of cork? What do I need to change from the stuff that I just showed you a few minutes ago to the new stuff that I have? I also am looking at chamois. Chamois is just another form of leather. So I'm going to see what it takes to engrave this. Typically, I clean my car with this stuff. And in the hobby stores, this stuff's really expensive, but the chamois that you get at your AutoZone or Riley's or other auto parts store is of similar quality, but typically you get 3 or 4 times as much. So I'm going to start shopping around for other places to buy this. Now, one of the things I did earlier in the week, and I didn't really talk about, is I'm actually doing something kind of strange. I'm actually coating the front of a mirror with black tempera. And of course, I'm using the high volume, low pressure detail gun that I got from Harbor Freight for 30 bucks. And as you can see, once this is dried, and this has now been 24 hours, we have a very, very even coating of the black tempera on the front of a mirror. And I'm curious to see what kind of transfer takes place, because normally you do mirrors from the back. Now, another thing that I'm trying over here is even something a little more insane. I'm using a modified Norton method, and I purposely didn't spray these. I used a brush because I wanted to see the difference between brush. Later on in the week, I'll take this other piece that's over here, and I'm going to go ahead and use the high volume, low pressure sprayer to get an even coat like this. But part of what we're doing here is we're piling up titanium dioxide. And I'm going to go do some 50 mil squares on this with various patterns and do some graphics on it on these test pieces to see, can we make titanium dioxide adhere to the surface of a mirror or a piece of glass. The difference being mirror obviously has a reflective surface, and when you flip it over, of course, it's got 3 or 4 layers of the mirror material and then several layers of paint and various other coatings on the particular piece that you're working on. So what's important about this particular test is its variable height, and it varies anywhere from 1/10 of a mil to almost 4 mils. And part of what I'll be looking at is, well, how does that impact the laser? Because it's going to have some change. The question is, how thin a layer do we need? And we go from thin to thick. What's the difference in adhesion from the titanium dioxide attaching to a smooth surface, this being mirror? I've been doing titanium dioxide quite a bit with various different tiles, so this is kind of a variation on that. So those are some of the things we're going to look at today. Again, this is mad science. I expect a lot of this to fail, but the interesting thing about the failures is you learn a lot about what you can do, and you're constantly looking for border and corner cases, because that allows you to take what you've learned from this particular example and figure out, well, what else can I do with this? You know, what happens once I get titanium dioxide on, and then I follow either from the front or the back of an engraved mirror that's been basically engraved on 2 sides instead of 1. And then what happens when I dab alcohol ink in there? What kind of interesting visual effects can I make with that? So that's one of the many things that we're going to tinker with through the rest of the week. As always, if you have suggestions, I'm certainly enjoy your comments. So let's get started. Okay, so the first thing we got to do is we've had 4 or 5 really heavy smoke days in terms of burning materials and so on. So the first thing we got to do is clean our laser. So let's get started with that. And I'm just going to let the video run so you can see what I'm doing. So out come the cotton balls. We'll be looking at the blast shield, and these are purposely made out of 5 mil black acrylic, because I'm studying the patterns of what really heavy 70 watt mode usage does. When you're in 35 watt mode, you don't really see any burning. The minute you get a 70 watt mode, this is the backblast coming back up from the surface of the material we're working with. And so we've done about 35 hours. Normally I do this every 7 to 10 days, but I'm doing a sooner than that inspection because I'm curious to see. We put a new one of these in just prior to doing all this work. I want to see how much damage we got over that time period. So we'll start organizing our materials here. Get our swabs out. One of the things we're going to take a real close look at is what shape is our lenses. We've done a lot of modifications to the filtering system and also the tilt angle and so forth. And this has been an excellent opportunity to evaluate extreme conditions when we're doing pockets with lasers. So we got most of our toys out here. So the first part is we're going to go clean our gantry. Have our handy dandy little storage place for our materials. This is gun cleaning material. This is gun oil. I like this stuff because of the materials that are actually used in the atom stack, and most other lasers are usually some form of stainless steel. So it's important to keep our things clean. I apologize, I'm going to do this in kind of a hurry, so you won't see everything I'm doing, but in the previous videos that I've done, I've got the detailed procedure pretty well documented. Now, one thing I'm noticing is that the top rail is really dirty from doing the work we've done over the last few days. I'm going to spend a lot of time cleaning and lubricating the rollers, the bearings, cleaning the focusing system, and of course cleaning all the rails. It's really important to get in there and do the detail cleans, because every time you have a piece of debris, you're creating a bumpy ride for your laser, and that's affecting your focus and the accuracy of whatever you're trying to create. So I'm wiping down the belts, I'm wiping down the rollers. I'm going to take my Q-tip and I'm going to move the rollers back and forth here so I get all the dirt off of them. And if you take a look at how much filth I just pulled off in a couple seconds, that Q-tip is filthy, and that's only from about 4 days or about 35 hours worth of running. So what I'm doing is I'm actually cleaning the groove in the wheel. I'm also cleaning around as much as I can the outside and inside of the face of the roller. And again, to do this, you just take the Q-tip and let the roller pass through it. And what we're doing, of course, is using the gun oil cleaner, or the gun cleaner, which has proven to be very good for doing this type of stuff. So now we're going to go clean out the wheels on the x-axis. And again, it's really important to clean the wheels. And you'll notice now that just after cleaning 4 rollers, that's really dirty. The other thing is in this corner, which is my X and Y0 corner, this is my primary work area. So most of the debris is right here. But with the very high airflow, the debris is definitely being sucked across. We're getting a very large percentage of the debris away from the laser, which has been the whole intent of all of the modifications that you've been seeing. The fun part is stretching far enough to get everything clean here. Now we're getting our Q-tip in here and cleaning all the crud out of the bearings and the rollers. And these things are filthy, even over this far. You know, this is 800 millimeters or 855 millimeters away from the other side of the chamber where the primary work is going. And it's just filthy. So we now have done our cleaning pass. And I forget what's in this gun cleaner, but it's probably some kind of nitro-oriented cleaner. So we've used the cleaner, we got everything loosened up. We've wiped off the excess, and now we're going back in the oiling pass. And again, with oils, it's important to lubricate. It's also important to always wipe off the excess. So, you know, this is for people that have non-modified lasers, this is a daily drill that you need to do if you want to keep your laser running. As we've been discussing over the last few videos, lasers don't last very long if you don't keep them clean. In a minute, we'll take the laser off of the gantry and we'll go through the normal laser process. But first, I'm going to finish getting everything lubricated. And again, you know, it's difficult to over lubricate, but you can. But it's very important to lubricate. And then most importantly after that is to actually wipe off the excess. So we've now got half of the y-axis lubricated. And one of the things we do is gently, from as close to the center as you can, move up and down the y-axis. And with this, this is of course spreading the lubrication, but it's also you're feeling for, do I have smooth running? Now in the y-axis, you're always going to feel little bumps. And those are normal. That's just the stepper motors going from one pole to the next. So there'll be a little friction, then there'll be a release of friction, and that's the normal action. Kind of feels like little speed bumps. So now I'm wiping off the excess oil. Now we'll go do the y-axis, move it back and forth, and you can hear it sounds different. It's now very smooth. And of course, we wipe all the excess off because, again, oils collect dust, and dust is your worst enemy, particularly in lasers. In fact, the worst thing you can do to laser is get oil in it. So it's very important to wipe everything down. Check the bell tension. This is still looking good. One thing I'm really pleased with this gantry system that Atom Stack has is I have not had to adjust anything in the mechanical chassis. It's been absolutely stable, which makes my day. So now we're going to go over to the other side, take our oil with us, and get the rest of the gantry lubricated. Again, I'm kind of doing this quickly because we got a lot of things that we're going to do today, but maintenance always has to be done. If you're not doing maintenance, you actually are risking fires and all kinds of other problems that you definitely don't want. So now we're going and oiling the opposite y-axis. And it's all running much, much easier than it was. And again, when you're doing materials that are really smoky, this is extremely important. You can almost eliminate any wear to your gantry and your mechanics by simply keeping them clean. Okay, so now we have completed our chassis lubrication and cleaning. The next part is we're going to fire up the vacuum cleaner and blow the dust out. And I'm going to turn my fans on, so you're going to hear quite a bit more noise, to the point where I'm actually going to put my ear protection on because shot vacs are loud. And when I add all that to all the other noise that's in here, makes sense to protect one's hearing. So we've got the 8-inch blower sucking 1600 CFM. I'm not going to turn on the intake fans. I'm now using the blowing mode to actually clean the intake fans. I actually filtered the intake. I use a very simple filter for that. What you can't see on the video is all the dust that's being blown by blowing through the fans. You have to be a little careful not to overspeed them. But the first thing I do when I start cleaning my bed is I blow air through, and then I'm looking for what other debris I might need to vacuum. But generally not a lot, because there's a huge suction on the opposite side of the chassis. And all I got to do is direct the air, and it'll go right out the exhaust stack. Now, particularly when you have a honeycomb, you've got to constantly check for places that have debris. And so when I'm going through and cleaning the honeycomb up, I actually reverse the blower, the shot back, and go back to vacuum mode. And honeycombs have several problems. The biggest problem is they're never level. And since lasers don't tolerate things that are not level because it affects the z-axis, we know that the sensitivity, at least of the diode lasers I'm using, are very sensitive. Less than 1/10 of a millimeter in variation of height screws up the focus, and you get uneven images, or your letters come out looking funny, and that's typically the problem. So now we've got our vacuuming on. Get rid of the headphones here. Now we're going to inspect the laser. Get our nippers out here so we can remove the tie wrap that holds the top in. So if we look at the top, there's just a slight hint of debris. The bottom has actually got more stuff on it because of the air that's coming up this way. But again, with the difference in the way this operates versus a stock laser, is its intake and exhaust are sideways. So if we look at the first layer, you can see a clear soot pattern, and if you flick it, you'll see the dust come out of that. So it's doing a good job of catching that, but there's not a lot there. Even after really, really, really smoky use. We'll grab our hex key here. And it goes without saying, anytime you're working on the laser, it shouldn't be powered. It should always have the power off. So now we'll wiggle out our data cable and our laser power cable. We have now loosened and removed the head. And as you can see, that filter is dirty. The top is dirty. So we know it's been trying to filter the air. And we're probably going to have to take the head apart because, again, this is the dirtiest work I've done with this yet. If we look at the bottom, basically that is heavily coated. But what it didn't do is it did not get in the bottom of the heat sink of the laser. The 1500 degrees that's right here never made it through the plastic. Because we have the tilt set up, basically only this side of the cone right about there has a little blast mark on it. But considering how smoky we were working, the only thing we got was a little burning of the furnace filter, which is to be expected. Now, as we take this apart, you can see all the dust that just came out. even though the air is going out rather than in, this shield is keeping the underside of the laser very clean. So again, now I'll start disassembling this. First thing I'm going to do is pop out the filter material. And these are filthy, just filthy. So when you're doing pockets or deep engraving or 3D work, these are going to get very dirty. And of course, as we look in the fan, we now have a lot of fan buildup. So we're going to have to take the whole assembly apart. And that was half the reason that we went and did the test cases that we did, is we also are continuously evaluating how well our filtering is working and what changes we want to make in terms of, in this case, probably filter material. Put that guy back. Get our little Phillips screwdriver out here. Another thing to remember from earlier videos is these little screws are a bear. And you want to make sure you've got a little cap. Paint caps work really well to put your screws in. And we are going to remove the fan, and I'm probably going to have to take the filter section off the fan this particular time because of the extreme amount of debris that was generated through the milling operations. Now, the amount of debris that was generated in this series of tests would have probably severely damaged lasers that have not been modified because of the parasitic gas flow and so on, and doing extremely dirty materials. Okay, so now we've taken the 4 side screws out. The fan is attached, and so we can now see that the inside of this is filthy. This is only from 30 hours worth of work, and that's even with a filtering system. So one of the things I'm going to be investigating is finding some other filters. One of the things you can do is, if you leave it connected, leave the fan connected, we can still take the rest of it apart. In order to clean this fan, we have to actually remove the screws that hold the fan to the filter housing. And it'll be very interesting to see what the tilt mod did in terms of the amount of material that was left. One of these days I'm going to have to get smart and get some T-hex wrenches. Standard right angle wrenches are kind of a pain for long screws. Takes a long time. T-handles you can spin with your fingers. Takes a lot less time. But with patience, both will get the job done. And again, it's probably a little hard to see what I'm doing here, but I'm just taking the screws that normally attach the fan to the upper mounting plate. That's what I'm removing, so I can actually take the fan out, and it's going to be a fair amount of effort to actually clean the poor fan. You really don't ever want to get your laser this dirty. And I constantly see on the internet, I just simply watch the top of what your laser looks like, and they're substantially dirtier than this one. I don't recommend using a power hex on these because you'll very easily strip the threads out, particularly when they're so dirty. So just gentle application of standard hex tool gets the job done. It just takes a little time. The other thing is I have my hand sitting on top of the laser because I'm trying to avoid putting stress on the very thin and flimsy power cable and connector that these fans are connected with. This particular fan is 44 to 54 CFM per minute, and it's a half an amp, and that's really, really thin wire to be pushing a half an amp with. Okay, so now we have the filter assembly and the top fan mounting assembly out, and we can see that's dirty, so we're going to get some cleaning material here. We use some cotton balls on this. Start cleaning in the frame up. And I think what I'm going to do is get the ear protection back on and get the vacuum cleaner and start sucking all this off. That's probably the quickest way to clean it. So you want to watch these little spacers because they do come off. Boy, that's really filthy dirty. I can't even vacuum it off. The problem with smoky debris like this is it severely compromises the system. Now I'm going in and starting to take a quick first pass at the fan. And we look at the blades and we look at the venturi. I'll show you that a little closer view here in just a second. So if we take a look, this is the side of the fan that faces down into the laser. And you can see all kinds of buildup on the blades, on the venturi, the mounting. On the front side, it's even worse. This would be the way it normally fits in the top. And so what we have to do is take a Q-tip and clean all this off. And when we talked about fans, getting a fan this dirty, it makes it heavy, it makes it draw extra current, which stresses all the components downstream. So we need to pay particular attention to keeping these clean. You notice the inside is really filthy, and that's going to take quite a bit of work to clean that. But again, part of the testing I was doing in the pocketing exercise was also testing the fan itself. Now, another real interesting thing I noticed is the fan bushings, which are these little guys, are coming loose. You notice some of them are flat and the other two are pushed out. So vibration from the fan is probably what's loosening that. So let's get some isopropyl alcohol out, and we're going to start going through and cleaning up The surfaces within the fan will eventually get to the heat sinks. Don't use this on lenses because it leaves smears. So one of the things you can do with your handy dandy paint dabber, paint can lid, is it's a good place to just put a little isopropyl. And so now what we're doing is we're going to hold the fan and we're just going to go in here and start cleaning. And again, this is one of the biggest problems with all lasers that have a fan and are air cooled, is trying to keep these fan blades and the inside of the fan clean. This fan was very close to seizing because there's so much buildup in the venturi area, which is what I'm wiping right now, that the fan was probably actually hitting, because you have buildup on the edge of the fan, then you got buildup in the venturi, and it's fairly tight tolerance. You probably have less than a mil between the fan blade and the venturi or the housing. And of course, if there's debris in there on both sides, the fan is very clearly going to slow down. That overheats the fan, but it does the same thing to the laser because your airflow is no longer efficient. So as we're cleaning here, the other thing I'm looking at is the leading edges of the fans. I'm looking for nicks. And again, you have to clean both sides of the fan. We're just on the front, top side right now. And I usually use 2 or 3 Q-tips. I go one pass of getting most of the stuff off, the really thick stuff. And then we carefully clean really every exposed surface, anything that's got any kind of dust on it. Okay, so the front side starting to look a little better. One of the things you got to clean is the back side of the fan mount because they collect dust too. That's kind of hard to see because it's actually underneath the fan blade. We flip it over. Again, being careful with the cable. Notice there's dirt even on the side of the fan. And again, this is just from basically 30 hours worth of use. And again, if you have a stock laser, you have to do this every day if you're doing dirty work. You know, if you're just doing light engraving or you're just doing image, particularly on a stable material, you're not going to see as much buildup. So now as we look in here, this is just filthy. This is so dirty that the Q-tip can't even collect any more dirt. So a little more alcohol. We're now getting the top layer. We have to remember to do both sides and then clean up the surface here as well. We just work our way around. There's going to be places you can't clean. Again, these fans were never designed for this purpose. And so one of the things in an ongoing conversation I have with various manufacturers is we need to start building lasers so they can be easily maintained. And the weakest area right now in all lasers is output lenses and trying to keep your fan clean. So this is an area where all the vendors need to get together and start looking at what customers have to do to try to keep their lasers alive. So we're now starting to get the venturi side clean. And remember, you have to clean all surfaces. And I'm probably going to take a second pass after I get the main cleaning done. the more dirt I can remove from the surface, the less it's going to attract more dirt. And as you can see, the blades on the backside are quite dirty. So as soon as we get all of this stuff clean, we've now got to go back and clean the backside of the fan blade. And I just stick my finger in it and I go down from through the bottom of the fan up through the blades towards the top, and I'm just wiping my Q-tip and trying to get as much dirt as we can off, particularly the edges of the blade, but you really have to get the whole fan completely clean. And that's what takes the most time. And again, stock lasers, you got to look at them every day. If they start looking like this, you've really put your laser at risk. So we're now starting to get most of the crud off. This helps the balance of the blade. It helps reduce vibration. As we notice, the little keeper nuts, these guys here, were actually backing out because the fan was vibrating so much because it was carrying all kinds of dirt that it was actually shaking enough to cause, actually you probably could even see surface defects in the actual images. Anything that affects vibration directly shows up on your image. Doesn't matter whether it's dirt on your rails, bound up rollers from dirt, and so forth. Anything that gets in the way causes imbalances, causes heating problems, and causes binding. So now we have cleaned both sides of the fan, we've cleaned the venturi, and I think we're probably good enough there. That's pretty clean. The hard part is trying to figure out how to clean the inside of the housing. Now I know how to remove the circuit boards and put heatsink grease and all that. I'm not going to show that because technically that would void your warranty. But again, for the vendors, which is funny, I'm getting a lot of vendors that now watch these videos. This is the area that is the weakest part of every laser that uses a top-mounted fan. I know there's some very exciting work done in one company, which I'm not going to mention the name of, but I am in touch with one of their engineers and several of their other folks. They're beginning to address this problem in a different way that you might expect, but I'm quite excited about that because we will see that sometime in the next few months showing up in some of their exciting new products. And again, this is what takes the time. All this has got to get out of here. Every bit of this is putting your laser at thermal risk. And this is so dirty, I'm not even going to blow it out first. I'm actually going to clean as much material as I can in the inside of the body of the laser. Bear in mind, I'm being very careful of the cable on the fan. And in fact, I actually wiped down the cables in the high-powered lasers like the 70s, probably even in the 48-watt versions. You need to keep everything clean. You need to get in anywhere you can get a Q-tip in and rub it clean. Down here we have some sensors. I'm not exactly sure what they are. I don't have information on that. But if they're dirty, they're not going to work well. And again, we're looking at the fan side or the top side of the laser. One of these days I'm going to figure out a way to get deep inside these things to clean them better. I'm hesitant to recommend putting them in an ultrasonic cleaner because A, most people don't have them, and you have to be extremely knowledgeable to use a device like that to clean something like this, because there's a lot of positive and negative actions that can come from using a system like that to clean. Although they can be used very successfully, it's generally beyond the experience of folks that don't design lasers. You know, if you're designing electronics, you know how to clean circuit boards, and you know how to ensure that you can properly maintain them. So I'm just going to take the fan, rotate it back, and temporarily just set it in place. We have quite a bit more work to do. We're now going to go grab our screwdrivers and start working on cleaning the lower side of the laser. Make sure I get the right screwdriver. Yep. So we've got our blast shield, and it's actually only held by 2 screws, which is all we really need. So as we go through cleaning the bottom of the laser, or the face, the part that faces the work, we're going to be looking for where did materials get up in the bottom of the laser. This is real important because that's where all the heat is. You're blowing cool air from the top, but you've got backblast and backflash both interacting on the bottom of your laser, particularly your heat sinks and part of the control board are all exposed. I should use shorter screws to be less turning. But next prototype of this will make an effort to make it a little more efficient to take apart. The other thing is, if I ever start manufacturing these filters, I will use keeper nuts so you don't have to worry about stuff coming off. So again, a lot of damage. This is like somebody sandblasted this, and this is the typical patterning that you see in 70-watt mode. It even frosted over the orange plex, of which I need to find a quartz window for that. It'll work better with the flame sensor. Right now, the orange-red partially desensitizes that. Now, as we flip it over, other than a light dusting, it's pretty clean. So that means that the normal backblast coming up from the material that you're lasing is having minimal effect. I think we can just use a cotton ball here. So that's good. It means that the bottom filter is doing what it's supposed to. Of course, we're pushing air down from the fan, and it's going out in all 4 directions, which is pushing the gas away so you don't get the parasitic flow. But we can also see the side facing the heatsink assemblies is going to be pretty clean. So let's go look at that real quick. So there's very little dirt, almost nothing. And yet we put this laser through pure hell over the last few days doing pockets, and that really doesn't even need cleaning. We're going to now go through and take a look at the output lens, which is the part I'm most curious today to see what kind of impact we've had with the filtering system. So we pull our little nozzle off here, and now we put it in bright light so I can see it. And guess what? There's nothing on the lens. This has been used in the most dirtiest way possible, and I'm not sure you can see it. I'll move it around a little bit here so you can see it. There's no pattern, none whatsoever. Let me get my specs on. I wish I still had my microscope, because then I could really take a detailed look. There's nothing on the surface. There's no pock marks, there's no burn marks. With my 2X glasses, I can barely see just a little dust pattern. So we'll go find a clean Q-tip. And now we're going to change our cleaning material. And my thanks to Adam Stack RMC, who turned me on to using a different cleaning material. I changed from using denatured, not denatured alcohol, but hydrogen peroxide, which is what I normally use to clean sensitive optics, to acetone. And the acetone dries a little faster. The key things that I look for when I'm looking for a cleaning solution is something that evaporates quickly. So we're just going to dip this in here and put our finger on the fan so we don't mess it up. And so, as we've covered in some of the other videos, just a light circular motion. And as you can see, that's clean. There's nothing coming off of this lens. So for those that don't think the blast shield and angling or tilt angling the laser doesn't pay off, we clearly are showing, even under the worst possible conditions, that these minor modifications have a big payoff. I'm also cleaning the sensors. I don't know why they even bother with this laser indicator. It's so far off, and every single one of them is different in their alignment. If you want to put a proper alignment in, you put one in each diagonal pointing to the focal point, and then it makes it really easy to focus the laser. So what I'm doing right now is I'm rubbing the swab inside, trying to get to as much surface area as I can to clean the dust off and gain an understanding of how deep the dust is penetrating. Actually, we know it's probably all over. Problem is there's lots of obstructions where I'm trying to clean in here, so I'm limited in my ability to thoroughly clean. The area that's most important is in the area where the printed circuit board, which is down here, is. You got to be very careful. There's cables down there. You don't want to disconnect them or damage them, but at the same time, anything we can do to wipe them clean will help reduce temperature. So the other part is, let's look at the focus limit switch. This is the lower limit switch, the one that you touch off that sets your 15 millimeter focal length from the tip of the cone to the work surface. Now the actual focal length is back in here, but from a practical perspective, all you need is a point of reference. Okay, so this came out pretty good. The big change is, we saw how dirty the top was, and we had to do a lot of scrubbing inside and so forth, and now I'm going to take the vacuum cleaner and run it in both directions to blow it out. First we'll put it in suction mode. Then we're going to take the fan actually out, but being careful not to damage its connector. I'm going to start backing in the pressure fan inside. And then this time, since it's so dirty, I'm actually going to fire up my shop air, and we're going to push some compressed air at about 125 psi to break up the dirt that is accumulated. Again, I apologize for the noise, but we'll just work around it. That's why I have my microphone on. So it's going to take a couple minutes for us to build up pressure, but we'll start cleaning anyhow. So right now we have about 40 psi. I'm going to blow the fan out first, but I'm holding the fan, my finger, because I do not want to overstress the bearing. When we're fully pressurized there, we're going to be about 100, 125 psi. One of the other things that I'm finding is I always inspect in here, and what I'm looking for is there any buildup of dust, because the air pump in these systems doesn't have any filtering. Yeah, let's just look at the buildup of filth on this. I'm going to clean that up in a minute. And I will go through the high pressure air, blow the tube out, and then I'll also blow out the cone. So that's clean. I'm going to wipe that down. I'm going to let this sit for a minute, build up some more pressure before we go back. So now we'll take and I can just use acetone. That'll work fine. What we're doing is removing any debris from inside the high pressure chamber of the cone. And this didn't really have any debris in it, and that's one of the changes that have been useful. And acetone's really good about taking the crud off the tip. And again, we can clearly see the mark of where the laser is hitting now as opposed to going straight back down the cone. And that's the reason why our output filter, or output lens as some people refer to it as, has that virtually no marks in spite of the extremely adverse conditions it was running in when we're doing pocketing experiments. So again, this isn't really necessary, but what the hell, we're cleaning, so let's clean. Because if it's clean and you start creating a debris pattern, you'll be able to see it better than if you have layers and layers of crud. And that's just from cleaning the tip of the cone. So we got this guy ready to go back in. So now we got enough air pressure build up. Just for fun of it, but now we start blowing out the side of the heat sink assembly. And there's no substitute for high pressure there. Even that still is not going to remove everything, but it will remove most of the loose stuff. The real danger here is actually the volatiles, which start as a vapor and then they condense on through the heat sink assembly. I'm still blowing a lot of dust out here. This is just filthy. Okay, so now we're going to go do the other end. And again, I have the fan off to the side so we don't stress it. So now we're cleaning around the lens assembly. I probably should have put the cone back on first. So this is the clean end of the laser now because of the glass here. And then the next thing to do, now that everything's blown out, is we're going to take the dovetail plate off. We're going to go inspect the limit switch. I think what I will do first is actually put the fan back on. I've still got a little cleanup I want to do in terms of wiping the filter assembly and the fan mount off. And again, this is the first time I've ever seen dirt actually caked on here. So in my operational procedures, when I'm doing pocketing, one of the things I'm going to be doing is daily cleaning, even with the filter and even with all the mods. And oddly enough, there's a correlation when you're using machine tools, you're doing CNC work, you have exactly the same problem. You have buildup of debris, and the number one thing in CNC work and most metal working, even woodworking, is you always want to keep your instruments or tools clean, because otherwise you develop tolerancing problems. The work you do becomes less accurate, less precise, because the dirt is causing you problems. You know, the buildup changes your mechanical tolerances, but it also screws all your bearings up. And of course, it leaves debris on your work surface. Okay, so you're starting to get there. Again, it just takes a little patience. And I'm actually using a swab that has ISO on it as opposed to acetone, because I have a mix of plastic and a mix of metal here. Okay, so that passes inspection. We've got all the dirt off. We've cleaned everything. So now we'll put the fan back on. And of course, I always have to check, make sure I put the fan in correctly, because you don't want the cable to bind. So it usually fits over like that. And when you have it correctly fit, it will actually seat all the way down. See how it's recessed here? That's correctly placed. Now, the easiest way to do the fan is actually to leave it out, but remember where you placed it. That way it's easy to see where the screws are going into the fan mounting plate. That makes it a little bit easier to go in and put the fan back in. Now I just have to figure out where I put my hex key. Tools are magical, they have wings. It's handy to have magnets because that helps you find things. Let's see, I may have to go find another hex key. Okay, we're back live. As you can see, we've got the filter assembly back in. We made sure that the cable is not binding the fan up, so that's kind of the critical thing you need to look at there. My switch is still okay. These switches are very fragile and they will definitely not last a year. It's one of the things I've talked to various vendors about. First of all, it was a stupid idea. This should have been under software control because it's a real pain in the ass to constantly have to interrupt your jobs and switch between the different power levels and the different beam widths. So note to manufacturers, make this software. So the next thing we're going to look at, now that we've found our hex tool, is we're going to take the focuser limit switch inspection and we're going to remove the dovetables so we can expose that. Remember, on this laser it's modified. It has a shim over here, which we'll see in just a second, and that's what's giving us the tilt angle. And the benefit of that, as proven again and again, even under extreme use, is that it leaves it clean. Referring, of course, to the laser filtering. So there's our screws. Here's the dovetail. Notice the burn marks down here. We cleaned that last time. This time we're going to take the little screws out. We're going to clean everything out under there. Here is the shim. Here are the two holes. The shim is 0.8 millimeters. It's nylon, so it's soft. It'll take a little bit of compression. This is the lower limit switch. When it touches, that's what's telling you where the servos are going to step up to 15 degrees from. This is a very fragile switch. This should be an optical switch, not a mechanical switch, because this is definitely going to fail in a relatively short period of time, particularly if people are not really diligent about cleaning. You're going to have nothing but trouble. So for these little screws, again, I always take them off over my paint can cover. And you got to be very careful not to strip these. Get a little different screwdriver here. Yeah, that's a little better. So these little bars just come off like that. I'll put that right there. We're going to take the other one off. And dirt debris definitely makes these screws stick. So you got to be very careful to not damage the screws. Okay, so note the position. The notch is up, facing this way. Take the other little bracket off here. Now we can see we actually have a lot of wear. And this is caused by all the hot debris coating this. On this particular surface, we'll just use acetone. That works as well as anything. Acetone is a good solvent for buildup of this nature. And you really need to clean everything because this thing just sits on the back of this. So we'll go back and clean that in a little more detail. But you can see all the dirt on here. And again, this was just done 14 days ago. I do this every other maintenance cycle. So that was dirty. Now let's go clean the rest of the stuff up here. Again, we're taking a little acetone in this case. I could use ISO just as well. What I'm doing is dissolving all the varnish and chemical buildup on here. And you'll notice that the end of this aluminum piece is actually burned. It's melted. In order to melt aluminum, you've got to be over 1,000 degrees centigrade. And there's big marks in it. That doesn't really affect its operation, but it does tell us a little bit about what the bottom of your laser faces versus the top of your laser when it comes to thermal shock and being coated with various debris. Now we're getting that pretty clean. But it has definitely marred the surface, no question about that. This particular laser head is only about 180 hours of operation total. Yeah, this stuff just really builds up. Is it critical to polish this thing? No, but it's just good best practice. If you're going to clean something, clean all of it. So the critical areas are where the cross braces come across. This surface right here, because that's what touches the little switch. And then clean the sides up so you don't get any binding. The freer that works, the cleaner your focus will be. Focus switches are not particularly accurate because they're very inexpensive mechanical switches. And so the accuracy and repeatability over time not only varies, but it can actually be as inaccurate as much as 1.5 mils with that particular switch and still be in what the manufacturer refers to as intolerance. So we got that one clean. Now we'll go clean this one. So the total time I'm going to spend on this might seem excessive, but remember we just went through a really, really severe test of all the systems when we're doing our pocket stuff. And again, if you're doing any kind of pocket stuff where you're doing deep engravings in 3D, you really do have to keep up on your maintenance. Okay, so now we're going to see if we can remember how to put this back together. So the tip that touches is right here. The part that hits the switch is right there. So the first thing we'll do is center. And I have debated whether I want to continue lubricating. And I think I'm still going to do that. Okay, we're back. We've now got the finger all cleaned up. Notice it moves very freely. Be careful not to over tighten the screws. So this is ready to go back on. So again, we have our spacer in the right place. And what we do is we just kind of shift this back and forth, testing. Then we start putting our screws back in. And so we turn them just till the screw starts to stop, so they're still loose. Because as we put the rest of the screws in, we're going to be checking see that the switch is working properly without any binding. And again, on this end, because we have the tilt mod, is we're only going to turn these screws about a turn. That's all it's needed. All you need is just a little compression. You have to make sure you don't cross thread them. Again, with these very small screws, you just barely tighten them, just so they're not loose. So we've completed all the cleaning. I'm not going to show the rest of the video of putting all the rest of the stuff back on, but we learned a lot about when we're doing pocketing or doing deep engraving of any kind or 3D engraving, we have to do a lot more maintenance. We need to do it on a more frequent basis, and we need to be extremely thorough on the cleanup. You know, if you look at the results, those are filthy. Now all of that is no longer in the laser. Okay, we're back live again. We got our laser all clean and put back together. That was the dirtiest I've ever had a laser. So what we're going to do now is we're going to build a 50 millimeter square. And we're going to test and see what happens when we use this particular image. We're going to do several different things. We're going to do a 50 mil graphic image. We're going to do a 50 mil line draw image. And then we're going to do a 50 mil square black image that we can use for testing various different areas of the test material. The test material is a piece of mirror that has varying depths of titanium dioxide. So the first test I'm going to do is I'm just going to run some text in it. So I'm going to go in and make a tool layer just so I can see what I'm doing. We're going to align the tool area. And in my laser bed, I have a square that I use for referencing where things are. This allows me to precisely position where my box is. Now we're going to edit the tool outline. We're going to make that 50 millimeter square so it's consistent with the previous work we've been doing for the last few days. Again, the reason why I use that is because it's big enough to actually see the effect of what we're doing. So now we're going to take and use under the arrange, we're going to basically lock that selected shape. Now we have a place we can do various different things in. Zooming up here. I think the first thing I want to try is let's just put a little text in here. And again, I'm just using a small area of the overall stuff. Let's go down and shrink it down. I want to make it so it's visible, but at the same time, I want to keep it fairly small. So we'll go with 7.5. So part of what I'm doing is I'm using a font that has kerns and edges on it, and I'm doing upper and lowercase. And then I'm just simply going to copy this and paste it, get as many of these as I can, because we know we have an irregular surface that varies as much as 4 mils of titanium dioxide just sitting on top of the face side of a mirror. And so this will allow us to kind of see what the differences in depth of the material we're using for transfer. And again, titanium dioxide, when we laze this, even at low power, should turn black. And then the next question is, well, how well is this really going to work in terms of different depths of titanium dioxide, and how well does it bond to the face side of the mirror? So again, 50 mil box, we got a bunch of tests in here. We need to highlight these here and put them on a different layer. Now we have them all tested. We'll make them black so it's easy to see. For this test, I'm going to leave them as they are. I might change a fill. Let's see what that looks like. We'll run the preview here real quick. I particularly chose this font because it has a lot of variation. And so you can see kind of what the fill is going to look like. I think the first pass will turn the fill off. The other pass we could do is invert, which means you're going to get black around the outside. We'll do that as a second pass. So we're going to turn fill off. We're going to stay in line mode, but we're going to use several different passes. So for this, we are in, let me double check what the laser is switched on to. Again, vendors, this is why it's stupid to have a switch on the laser. Yes, we are in 35 watt mode. This should be done in software. It makes it much easier. It means that I can actually change the width of the beam in the programming as opposed to having to constantly manually change it. So for this test, we're going to use 20% 35 watt mode, single pass. Let's open up our layers and cuts property sheet here. So maximum power 26,000, that's a good starting point. We're not going to do any increments or anything like that. So we're going to go to the simplest test case pass. Let me go ahead and frame this real quick. The good thing I checked is I didn't position the materials correctly, so let me go correct that real quick. Okay, now we're in my normal working position of 51 and 200. The other reason why I put it there is just a convenient place. And when I'm taking videos, I can see if I have it put down in the corner, I have to put the camera on top, and then you can't see as much. So that's what we're going to start with this. So we'll go frame it one more time, verifying our range to target. That looks good. And we're going to use, we'll check the Z, which is at 14, which is actually 15. So that's good. So we're putting it at the autofocus position, just as we've done all our previous testing. Now, if I was in an engrave and I wanted a really sharp engrave, I would actually move the laser farther away from the surface, so it's a 20 versus 15 mils from the surface. So we're going to go ahead and start that. This will run very quickly, but I'm going to stop the video here and we'll check it when it's done. Okay, so the result was interesting. We didn't see any black marks on the media, even looking at it straight down. So we need to either decrease the speed or increase the power. Because we're using a mirror surface, we want to probably reduce the speed. Again, the lower the power when you're doing the face of a mirror, because it's fully reflective, even when you have the coating on it, we want to keep it as low as possible to keep any opportunity for backlash, which can damage the laser, even though we have the 7.5 degree mod on this. We want to make sure that we do this at the lowest temperature possible and the lowest backlash. So we're going to leave the power at 20% of 35, which is pretty low power, only a few watts. And what we're going to do is do the same thing, and we're going to change one parameter. We're going to go to cuts and layers, and we're going to go and reduce the speed down to, let's go for 1800. And then we're going to restart this. And so this will run for a little while. We'll check on it when it's done to see if we start marking. Okay, let's take a look. As you can see, we've reduced our speed down to 600 from 6,000. We have the power setting at 20%, and that's to keep the backlash and the temperature as low as possible. We are now starting to see the titanium dioxide start to bond with the mirror surface, and we're actually starting to get a black impression. So the next pass we're going to do is we're going to turn film mode on with the same settings and see what that does to deepen this. And the other thing we're seeing is we have a tremendous amount of z-axis variation in the thickness of the titanium dioxide, which was mixed with alcohol, and now the alcohol is all evaporated, dried for 24 hours. So the only thing that's keeping it in place is actually moisture. So we're going to go ahead and run this again and see what kind of result we get. Okay, so we're now running our third pass. Power is still at 20. We've dropped the speed to 600. We've gone from line mode to fill mode. In the fill mode, we basically have the defaults, but in the next pass we're going to do right now, we're running a 254. We're going to change lines per inch to 600. And what we're looking at is, are we increasing the bonding and increasing the darkness of the titanium dioxide to the glass surface, even though we have widely varying depths of the titanium dioxide. So this is going to run about another 7 or 8 minutes, and then we'll run the 600 pass. So it's interesting. When we went to fill mode, of course we got a much better looking text. It's also a lot darker. And again, we're at speed 600, 20% of 35 watt power. And so this is looking promising. I'm going to save off these settings. I will, in the next day or so, prepare some additional pieces of mirror, and I will put on a very smooth coating of titanium dioxide. And what will be interesting as we look at this, we have areas that have very deep piles of titanium dioxide and areas that have very thin. And once we've cleaned this up with water and wiped it down with acetone, then we'll see if any of it actually held. So the next test we're going to do is we're going to copy the tool square so we know its size. We're going to find a fairly simple line drawing to put in that, and then see what that does. And then if we have room for one more in this row, we'll take a simple graphic image and see how that does. Okay, just for fun, we did a 600 DPI test. And we're really starting to get a fairly well resolved burn of the titanium dioxide. The big test, and we're all done testing this particular piece, is the cleanup. Titanium dioxide is notorious for coming off the surface when you clean it with warm water and then follow it up with acetone or alcohol. So that's one of the other things that we want to look at. So we're now going to set up for a line test, which we're going to do another 50 mil square right next to the text one and see what kind of results we get from that. Okay, so we've now set up a vector drawing. This is an SVG file. Has multiple layers. I think what I'm going to do is turn all these into a single layer, and then we'll burn this and see if we get clean lines. Okay, so we're now setting up for the new pass. We're going to go with the speed of 400. We're going to slow it down a little bit because we're kind of changing what we're doing. And I'm going to be looking really closely at the detail that we get out of this. And again, we're just right next to the previous image or the previous text that we were playing with. And we're working with titanium dioxide that varies from 1/10 of a mil to almost 4 mils deep. So we can kind of see the effect of depth of titanium dioxide as we're trying to apply it to the mirror face. So we'll go do a quick frame just to make sure we're in the ballpark. And yes, it still likes us. So we're going to turn off the previous output, so we just have the one we're working with. And now we're going to go ahead and start running that. So here we are side by side. We've got 5 passes on the left with the text, and we're getting pretty good titanium dioxide burn. We've just done a single pass at 400 versus 600, same power, 20% at 35. And we're actually seeing evidence of the fact that it looks like it might actually be trying to bond. Again, we have tremendous variation in the depth of the titanium dioxide, so we need to think about that as it applies to this. Normally you would have a very flat, thin layer. This layer is variable depth. Okay, now the setup for the next pass is we're going to do something a little different. Normally that SVG would not be done with fill, it would be in line mode. But what the heck, we'll try it, we'll see what it does. And one of the things I'm going to be looking for is consistency of the fill. I'm setting it up for a speed of 250 to see what the lower speed will do. I'm looking for a little more dwell time on the titanium dioxide to see if we can improve its darkness and its fusion to the glass. And then I'm running at 300 dots per inch. When you're in line mode, dots per inch don't really have much meaning. So we're going to now give that a pass. Now, of course, it's increasing the runtime, but that's okay. As you can see from putting the fill in, the little Christmas trees and stuff are filled. You're not going to see the elk up there because there's a couple of discontinuities and it's not filling it up, so you won't see that. So we'll see kind of the mountain with the trees and the clouds. And here it is complaining, which is good. Okay, let's take a look. So it's real interesting. This is the second pass, and this is with fill mode on at 300 dpi. Everything else is the same. I was very surprised how well this worked. Now, what will be interesting is when we wash the titanium dioxide off to see how much actually bonded. But we're now on the front surface of the mirror, putting a black image across the mirror, which I don't think I've seen done, but it's going to be very interesting to see how this turns out. The next thing we're going to do is we're going to go find another spot on this piece of test material. And we're going to use a graphic image the same size, same parameters, and see what grayscale looks like. Okay, we're getting ready to do our first grayscale image. And we've gone ahead and we're going to run it at 200. We're going to go down and set grayscale up. We're going to go 300 dpi. I'm going to go minimum power of 2.5. One of the things I found is that you actually get a better grayscale image with 2.5 than you do with 0 for some reason. It probably has something to do with the fact the laser is not quite high enough in power to actually do anything until you get about 2.5%. Again, we're in 35 watt mode. We're running half the beam size. Line interval is 0.0847 or 300 dpi. 2.5 overscan. We have dot width correction to 0.80. So we'll do a quick frame here and make sure it shows up in the right place. And yes, it still likes us. And so we're going to change the image so it's a different layer. Now we can keep all our layers straight. So let me go in and fix the properties page here real quick. So 200, 20, 300, grayscale, dot correction. So we're good to go there. Let me go close the top here. And away we go. So we'll take it a minute to think about this. Now it's starting to process it. And it's probably going to take 2 hours. That's a long time. Well, we'll see. We'll come back in 2 hours and see what's going on. Okay, we're back. We have a mountain of snow of titanium here, but we are actually seeing what looks like some bonding. Now, one of the things I changed, I went about halfway through and discovered that I'd forgotten to set 2.5% for minimum power. So when you get to this point, this is all at 20. And then we're going from 2.5 to 20 in this part. And it'll be interesting when we wash all this off to see what this actually turned out looking at. The other thing we did is we changed from 300 dpi to 200 dpi because the runtime was going to be about 4 hours. So this took about almost 2. So again, we've now done a graphic image with grayscale, we've done a vector image, and we've done a text image. So we're going to now, as we're basically done burning, we're going to go recover the titanium dioxide and clean this. Then we'll take a more detailed look at it. Cheers everyone, Cloudfather here. We've just completed an interesting day of testing. We have a piece of mirror, and what we've done is instead of engraving on the back, we put titanium dioxide in the front. We tried text, line art, and graphic art. We made a little mistake down here where we didn't set the minimum, so we were straight 20 trying to do graphics. Once we set the minimum, we actually started getting a fairly good engrave. Well, that's going to need a little tuning and speed, maybe treating the grayscale a bit. But one thing we did learn for sure is it is possible. And what's on here is this is the effect of titanium dioxide on a mirror. Other experiments will be done to see if we can darken it. But the thing to remember on this particular piece is we purposely built a very uneven titanium dioxide surface just by dabbing titanium dioxide on top of this piece. So let's talk a little detail about the titanium dioxide mirror. Now normally on a mirror, we use the back surface. So We're shining the laser back here with a reverse image and creating a pattern. What we did that was different, that I haven't seen anybody do before, I'm sure somebody probably has, is we put a random thickness layer of titanium dioxide on the surface, let it dry for 24 hours. We use 91% ISO to mix this with. We filter it, and then we paint it on with a brush. Now, the normal way I do this is I do a very thin layer. I use a high volume, low pressure detail sprayer, normally used for automotive painting, because it can handle large paint particles and do things like metallics. And what I shoot for is to try to get a 0.1 mil even layer across the surface, the same way I do with tempera paint on regular glass. But in this case, we're building a bunch of mountains randomly all over the test piece, so that we kind of see what happens in various steps. At the same time, we're testing to see if titanium dioxide will adhere to the front face of the glass, the mirror being on the back side here. So as we look at the results, this really was pretty interesting. I don't know how well you're going to be able to see this. We got a little bit of burn through, but that's because we didn't set our minimum setting to 2.5. We ran 20 and 20. But once we got that set properly, we started getting a pattern. Remember, this is grayscale, and grayscale does not work well at all for titanium dioxide. You would have to do all kinds of layers. You might even have to recoat it to get depth in it. But for wood and other things like that, other types of materials, titanium dioxide is pretty useful. Now, in terms of our text tests, we did both line and fill mode. And you'll see where there was enough depth of the oxide here, but not enough here. So there was very little adhesion. We also tried different sizes. We tried things that are close together to see kind of, as we have this irregular surface of titanium dioxide, it would even stick. This was a line drawing that we did. We made 2 passes. We made a line pass first, and you could clearly see the outline of everything. And then we did a fill pass, which we normally wouldn't do with this because it's not really designed for that. We miss half the mousse there in the middle. But we got nice, distinct, clean titanium dioxide burns on top of the glass, and we did not go through the backing. In fact, the mirror under there is probably fine. So we have proven that should you have the interest, you could do that. Now, if I was doing a pattern with titanium dioxide because I wanted to put alcohol ink in it, basically I'd do it all this way, and then I put my blue and yellows and pinks and whatever in each of the little pockets. And this gets back to the last few days of work we've done in terms of trying to mill with a laser or create pockets. Very shallow pockets are great for putting very fluid paints like alcohol ink, which is technically a resin, and things like acrylic paints. So that was a very interesting experiment. None of it was expected to work. This is just run-of-the-mill Lowe's hardware glass. You can see my Fred Flintstone glass cutting. I'm getting closer to making straight edges and round corners. It's going to take me a while. But I thought it'd be interesting to cover this example today. Tomorrow we got a whole bench full of additional materials. We got 6 different types of leather, some corks. I may try some more mirror, and I'll probably try some glass over the next week here. We're going to use the same type of process to look at where we dial it into and then how far can we move it in the different parameters to improve the quality of our end product. So thanks for watching. Cloudfather out.